How's it going, everyone? Mr. Geyser here with Lesson 10A on trigonometric equations and inequalities. In today's lesson, we have 5 main skills and learning objectives. The first being, we want to try and find those general solutions for trigonometric equations. 2, we want to try and solve trigonometric equations of multiple angles. 3, we want to try and solve trigonometric equations in quadratic form. 4, we want to use factoring techniques and technology to solve those trigonometric equations and inequalities. And 5, we just want to try and solve those trigonometric inequalities. In this lesson, we consider trigonometric equations and inequalities. Equations that contain trigonometric functions can be used to answer periodic behavior in our world. We can predict the tides, moon phase, seasons, breathing intervals, and more. A trigonometric equation is an equation that contains a trigonometric expression with a variable that are satisfied only by some values of the variable or possibly have no solutions. Inverse trigonometric functions are useful in solving equations and inequalities that involve trigonometric functions, but solutions may need to be modified due to the domain restriction. In example 1, consider the equation sine x is equal to 1/2 on the interval of -3 pi over 2 to 7 pi over 2 shown below. Notice that the x-coordinates where the graph of y equals sine of x intercept the line at y equals 1/2 are the solutions to the equation above. In part A, can we find those 5 solutions shown? Well, it's pretty easy. We just want to try and locate these 5 different x values where those 2 lines happen to cross. Now, as a reminder, these lines here are not the equation of sine x equals 1/2. Rather, this sine of x wave is crossing that y equals 1/2 5 times between that interval. Between that interval means we have 5 solutions there. In general, for those 5 solutions, we can find that it goes from -7 pi over 6 all the way to 17 pi over 6. In part B, how do we represent all the solutions to the equation? Well, if we take a look and try and break down these points, notice how this first point here really is just repeating every 2 pi, where the period itself is 2 pi. So we know that this point, where it's the solution on our graph, repeats every 2 pi, but it doesn't repeat every x amount for here. We have to have a second type of repeating equation where this second point happens to repeat 2 pi away from before and after. Just looking at that first point here, we can write that general equation as theta of 1 is equal to pi over 6 plus that period of 2 pi times k. Notice where that pi over 6 comes from. It's just that horizontal displacement or that phase shift of this solution here, where if we add 2 pi, we'll get that next point. We can write the second theta equation here, where this value of 5 pi over 6 is just coming from that distance from the y-axis for that second point. So let's break down both of these equations just for a second. If we grab that first equation here for theta 1 is equal to pi over 6 plus 2 pi, if we were to plug in k equals 0 to find the first time where we get that solution, really, we're just kind of canceling out that second term there, and we find that that first solution is that pi over 6, where k equals 0. If we were to increase k just by 1, we're really just adding a single period to this kind of equation. And we can find that next point of 13 pi over 6. If we were to continue to increase k by 1, we can find every additional point that repeats at that position. If we were to make k negative, -1, -2, -3, we would find every point that repeats 2 pi away in the negative direction. Let's show that example with our second theta equation. Notice for our second theta equation, I'm going to grab that middle one here and make it equal 0. That first one just kind of cancels, or that second term cancels out for k equals 0. And we find that that second theta, the first instance of that solution, occurs at 5 pi over 6. Notice that for both of these k terms, -1 and 1, when we solve these out, it really is just 1 period behind and 1 period ahead. We can find these general solutions to find when those equations happen to equal each other. The 2 equations that we're trying to find to make them equal each other is this sine of x equation and the equation of y equaling that 1/2. In example 2, we want to solve the equation by using the unit circle, and we want to give the general solution. For this first equation here, we have 2 cosine x minus 1 is equal to 0. So first I'm just going to rewrite that equation there, and I want to try and get x by itself. Those first two steps there, I'm just going to add 1 to both sides and then eventually divide by that 2 to get cosine of x is equal to 1/2. From here, I still want to try and get x by itself. So I can use this inverse cosine equation to simplify out that x. Notice what happens here. These two cosines simplify out, leaving us just the argument inside our initial equation, where it just happens to be x, while the right side of the equation now is that inverse cosine of 1/2. From here, we still want to try and solve out what that inverse cosine of 1/2 is. And from that previous topic, 3.9, we know how to solve these. We just set that inverse equation equal to theta, and then we want to determine when that cosine of theta is equaling that argument of 1/2. We can find that that theta, the first time that it occurs, happens to be here at that pi over 3. The second time that it occurs is this 5 pi over 3 down here. From here, we can use these two initial points to create those two general equations. For that x1 there, we take that pi over 3 plus our period times k, and for that theta 2, we take that second initial point of 5 pi over 3 plus our period of 2k, plus our period times k, where k is going to be any integer value. The solution for this equation here is both of these two equations. We want to try and find these general equations where 2 cosine of x minus 1 is equal to 0. For example 3, we want to solve each of these equations, and we want to give that general formula for all the solutions. In part A, we want to try and solve sine of x, where that's equal to negative the root of 2 over 2. My first step here is just to rewrite that equation, and I want to try and get x all by itself. I first want to try and take the inverse sine of both sides, where this is going to simplify out just the x here, and this other side now is the inverse sine of negative root 2 over 2. Well, so now we want to try and solve for that. So now we just want to try and solve out when sine of theta is equal to that negative root 2 over 2. So when does that occur? Well, we're just going to bring up our unit circle just one more time, and we can find when that y value on these points here is that negative root 2 over 2. And it occurs at this 5 pi over 4 radian and this 7 pi over 4 radian. I can take these two initial radian values there and use those as my solution. As a quick shortcut for finding these points here, I'm going to use these kind of diagrams throughout this lesson to showcase where I'm grabbing those theta values. Once I grab those theta values there, my x1 being that first radian of 5 pi over 4, my x2 being that second radian of 7 pi over 4, I just want to add a period length to both of those and then place that k value at the end to indicate that these solutions here are infinite. We can find an infinite number of solutions here by just increasing k that infinite amount. 1, 2, 3, 4, 5, all the way to positive infinity or all the way to negative infinity, but we'd still find the solutions to that initial equation in part A. In part B, we're given this 18 cosine of x minus 7 is equal to 14 cosine of x minus 5. Now I want you guys to use that pre-algebra kind of like knowledge base where we want to take this single term of 14 cosine of x here, and we want to try and combine like terms with that 18 cosine of x here. These two happen to simplify down to that 4 cosine of x. We're just moving those terms around. Now we want to try and get rid of that negative 7, so we're going to add 7 to both sides, and eventually we get 4 cosine of x is equal to 2. That last two little steps here is just to divide by 4 on both sides to get cosine of x is equal to is equal to 1/2 here. And now we want to use that inverse technique to take the inverse cosine of both equations to simplify out that cosine so that the argument of x is now by itself, and the right side of the equation is now cosine or inverse cosine of 1/2. I'm going to bring that up to the very top right here, and now we just want to try and solve out when inverse cosine of x is 1/2. Well, to solve that out, we've got to rewrite that equation there to cosine of theta is equal to 1/2 and determine when those theta points happen. Well, they happen at these positive values here. And I know that it's going to be at that pi over 3 when x is going to be 1/2, and at this 5 pi over 3 when x is also going to be 1/2. And I'm just leveraging that knowledge of the unit circle here to find what those radian values are. Once I find these two initial points, I'm now able to derive these general equations by making x1 equal that pi over 3, that x2 equal that 5 pi over 3, and now I'm just adding a single period length times k to each of them. These general equations will be used to find the solutions for this problem here whenever our k value is plugged in to 0, 1, 2, just some integer value. Now, for example 4, we're going to use a calculator to solve each equation. We want to make sure to round our answers to 2 decimal places. In part A, we're going to try and solve out that tangent of x is equal to 5. First, I'm just going to rewrite that equation there and just solve for x. I'm going to use that inverse property where I'm taking the inverse tangent of both sides. I end up simplifying out that tangent, so I just get the argument by itself, where x is equal to the inverse tangent of 5, which I don't happen to know at the top of my head. So I'm going to pull up my TI-84 calculator. To grab those inverse trigonometric equations, we're going to use that second, and then grab that trigonometric equation. The inverse option is just by selecting it here. We then select 5, and we find that the inverse tangent of 5 is that 1.37. We can bring that back into our slides, and we can now write that general solution where we're adding a single period of pi, because tangent's period is just pi times k. To make a little bit more sense of this equation just for a second, what we're really saying is that when we're graphing this tangent function of tangent of x, we just want to find the equation to determine when it's intercepting at that y equals 5 line. We found that very first solution of 1.37, and now if we add or subtract a pi, we find each of these other x values that passes through this y equals 5 and our tangent equation. If we take a look at part B, we want to try and solve out cosine of theta is equal to 0.6. I'm going to rewrite that equation real quick now, and we just want to use that inverse property, get theta all by itself. And again, I just don't know what the inverse of cosine of 0.6 is off the top of my head. So I'm going to bring up my TI-84 calculator. I'm hitting second again, going to cosine, and once I select that, I get that inverse cosine. And now I type in 0.6 and find that my one solution is 0.927. Once I bring that in, I can say that my theta here is equal to 0.93, and notice that since it's cosine, we should have a second solution because it's that periodic wave. So we should have some other theta value that shifted some amount from this value here. Well, if I bring the graph in for both of these equations, this first graph here is that cosine of x. This straight line is where y is equal to that 0.6. And now we want to try and find when that second x value is. Well, notice that for this value here, it is just that phase shift of 0.93. And notice this pattern. This other value for x here is just a phase shift of 0.93 from the end of our graph. And we know intuitively that these cosine functions have a period length of 2 pi. So to find this second value, all we really need to do is take 2 pi minus that initial value that we find. If we type that into our calculator, eventually we'd find that it equals 5.36 here. And now we can write the two general equations for cosine, where we're just adding that single period length of 2 pi times k. Now, we turn our focus on finding solutions of trigonometric equations for that interval where x is greater than or equal to 0, but still less than 2 pi. Let's begin with some factoring examples for simple trigonometric functions and then move to multiple angle equations. In example 5, we're going to try and solve the square root technique on that interval of 0 to 2 pi. In part A, we're given that 4 times sine squared of x minus 1 is equal to 0. We can use those simple techniques to add 1 to both sides, then divide 4 to try and get sine squared of x is equal to 1/4. Notice, if we take the square root of both sides, sine squared of x just becomes sine of x. On that right side, the square root of 1/4 becomes plus or minus that 1/2. We now want to try and find when that x value for sine, that theta, gives us that y value of 1/2 or negative 1/2. We find all those y values around our unit circle, and then we grab the radian for each of those y values there as our solution. I'm going to move up that kind of work there and just say that x is equal to each of these 4 radians between that interval of 0 all the way around to 2 pi. Now let's explore part B, where in part B we're given 3 times tangent squared of x minus 1 is equal to 0. We're going to use that simple technique real quick to add 1 to both sides, divide by 3 on both sides, and now we're left with tangent squared of x is equal to 1/3. Notice that when we take the square root of this trigonometric equation, we're just left with that tangent of x is equal to that square root of 1/3 plus or minus though. I'm going to bring this up here. I don't really like that root of 1/3. I'm going to simplify it out so I can find that on my unit circle. Really, that root of 1/3 is equal to the square root of 1 divided by the square root of 3, which is really just 1 divided by the root of 3. I don't want to have a radical in my my denominator here, so I multiply by root 3 over root 3 to simplify out that radical, and then I get that root 3 over 3. I need to remember that I'm still adding or subtracting it while I'm trying to find the positive or negative value of it. And if I bring this different version of the unit circle, it tells me all the slopes of these terminal rays being projected from the center to these P points around each of our main radians. These values here are the slope of those lines. I still want to try and find when my tangent value is plus or minus that root 3 over 3. It happens to occur in these 4 different locations where my theta, the thing I'm plugging into my trigonometric equation, is either pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, in example 6, we want to try and solve out these 2 equations that look very similar to quadratic equations. In part A, we're given this 2 times sine squared of x minus sine of x minus 1 is equal to 0. Once we rewrite this here and kind of heighten those sine of x's into red, we can kind of see how it looks like a quadratic equation. From that quadratic equation, we can simply factor it down to this step here. Now I do want to pause here. If you don't feel comfortable factoring these quadratic equations from this first to that second step, that's going to be a different type of practice that isn't shown in this lesson. For here, once we're at this stage, I want to showcase how we can solve out these trigonometric equations. After factoring these quadratic-looking trigonometric equations, we now want to try and solve each of these parentheses here and set them equal to 0. For that left side and that right side, we can simply solve those out to be sine of x is equal to negative 1/2 and sine of x is equal to 1. Very quick solves. And I want to try and bring in my unit circle here and just find when my y values equal negative 1/2 or positive 1. It only really occurs in those 3 different locations, and the answer to part A is where they're at with the radian value. It's these 3 radians that I would plug in for x when I plug them into sine, where they would then equal that 0 value. Let's take that look one more time at part B. At part B, we want to rewrite this equation 6 times sine squared of x minus sine of x minus 2 equals 0. We can see that it looks like a quadratic equation, so we can factor it as such. And again, if you don't feel comfortable factoring quadratic equations, there's a different lesson for practice of those types. Once we're at this stage, we now want to try and solve each of those parentheses where we're setting that argument equal to 0. Once we solve these out, we get that left side is our cosine of x is going to be equal to 3 or 2 over 3. On that right side, cosine of x is equal to negative 1/2. I know intuitively that I don't have an exact value that's 2/3 on my unit circle, so I can just plug that into my calculator, the inverse cosine of 2/3, and I get that first x value of 0.841. I want to leverage that knowledge from example 2, where we can just subtract the period length of 2 pi from that initial first value to find that my second x value is going to be that 5.442. For this right side of the equation, I'm still given a value here where I know intuitively I can remember where those x values are on my unit circle. And it happens to occur here at that negative 2 pi over 3 and that 4 pi over 3. I acquired those 2 answers from that unit circle where our x values were equal to 1/2 here, or negative 1/2 here. In example 7, we want to use the factoring technique to separate these trigonometric equations. First, we're going to rewrite that sine squared of x is times tangent of x is equal to 2 times tangent of x. I want to treat that like a term where I can subtract it over from both sides to bring everything to that left side of the equation. And I can notice that I can factor out a tangent of x from both of those terms. I'm going to bring that up here real quick. And I can treat this just like that other 2 equations here, where I want to try and solve when tangent of x is equal to 0, or when that argument of sine squared of x minus 2 is equal to 0, treating this just like a quadratic equation. I also know intuitively when tangent of x is equal to 0. It's going to happen at one of those two key points when x is equal to 0 or x is equal to pi, when it's like very flat, that terminal ray is being shot right out from the center. For the right side of this problem, we're given this sine squared of x minus 2 is equal to 0. We want to try and solve it out, so I'm going to do it pretty quickly. I'm going to add 2 to both sides, then take the square root of sine squared. I am going to get that square root of 2 plus or minus as my answer. And if I type this into my calculator pretty quickly, I end up getting sine of x is equal to plus or minus 1.41. And I know that the range for my sine of x here is only between -1 and +1. So this negative and positive 1.4 value falls outside my range, and there's no x value that would give a solution for this side of my quadratic equation. My only two solutions are when x is equal to 0 or when x is equal to pi, because that solves out my tangent trigonometric equation. In this lesson here, we learned how to factor out these tangent equations by treating them very similar to quadratic functions. We learned how to write those two solutions for these trigonometric equations where they happen to equal a specific value, and we discovered how to find these factored versions of our trigonometric equation. Thank you very much for joining me. If you have any questions, please leave them in the comments down below, and I look forward to seeing all of you guys in class. Take care.